ladies and gentlemen. My name is Mujahid Muhammad. I'm a first-year PhD student at Birmingham City University. My research area is security issues in the LTE-enabled V2X communication systems. So, the content of my slides are, first I will provide a brief introduction into V2X communication system, although you have been hearing of V2X in the previous session, in the previous speakers, but I will also have a brief introduction about it. Then V2X applications and services, V2X service requirement, the threats and attacks that are related to V2X, and also the network security and privacy issues in V2X systems, then the proposed solutions and further work. So vehicle to everything communication is referred to as communication between connecting vehicle to everything. That is vehicle to vehicle, vehicle to the infrastructure, to the roadside infrastructures, as well as vehicle to the network and the vehicle to pedestrians. It is one of the fastest growing type of connected devices after smartphones. Currently, the evolution of technology in which the vehicle is equipped with an onboard unit that can be able to collect data, sense data around the environment, and also transmit data in real time between a vehicle, between the network, and also a pedestrian that has a handheld device. Also, the V2X is the core areas of the IoT Internet of Things, and also the 3GPP have approved the support for V2X communication, which is referred to as LTE-enabled V2X or LTEV. That's the name, that's the convention which has been used. It is being supported in the release 14, 15, and as well as 16, which is also a part evolution to the 5G network. So the applications areas of V2X communication, which you have already heard about them, at the road safety and traffic management, infotainment, as well as the autonomous driving system. So these are the 4 key areas in which V2X applications have been used. So the V2X, the sole idea behind V2X is to reduce road accident, as well as creating efficient traffic movement, reducing CO2 emission, fuel consumption, as well as enhancing the comfort of road users using the infotainment services. So this is the architecture of an LTE-based V2X communication, in which it has 2 types of communication. One, which is the V2N, which is vehicle to network, in which the vehicle is connected to the radio access network of the LTE through the E-Node B. Then the traffic will be relayed down to the LTE core network through the MME and the HHS and down to the V2X application server, in which it's been defined in the architecture whether it can be part of the LTE core network or it should be remotely connected. So, the interface this is either a unicast or a broadcast through the either uplink, downlink communication via the UU interface, which is the standard LTE interface that is being used for the radio communication. So, and another form of communication is the V2V, which is the direct communication between the vehicles, which will be supported through the LTE direct, which is referred to as D2D communication. So there is also communication between the vehicle and the maybe roadside unit, which is the RSU, but that type of communication is not being passed through the standard LTE core architecture. So the key advantages of using LTE, which is over the DSRC, is one, it has an enhanced coverage. The LTE has already an enhanced coverage, support for high mobility, and also high density support, in which it can be able to support due to the introduction of small cells deployment, micro cells which can be deployed across the cities where you have densely populated vehicles. So those small cells can be able to support vehicular communication. Also, the widely deployed infrastructure, because the cellular network is already been deployed, it's already been in use for mobile communication and what have you. And also, there is native support for V2N by leveraging the existing cellular network. And also, the third advantage is another advantage is the V2V support potentially through the direct D2D technique. The transmission mode can either be a unicast between the network to a vehicle or a broadcast in which the application server will relay a message through the LTE core network as well as the radio access network, and then it will broadcast to the nearby vehicles that are within the surrounding cell. And also, yeah, this is the strong evolution path towards 5G. So these are some key advantages in which LTE enable V2X communication offers more than the DSRC. So as you have heard it already, characteristics of V2X cellular vehicular communication, in which it needs high mobility dynamic network topology, because vehicles can add to the network and they can be able to join and remove at the same time. So, and it is unbounded network size, heterogeneous environment where we have high density area and low density area, and support for low latency. Low latency is very important in V2X communication, which is also going to play an important role with regards to the security issues in V2X communication, high reliability and wide band ranging and position. So this comes to the V2X security issues that are related to vehicular communication. These are some of the threats that have been identified from the literature that will affect some of the key security components, which are availability, authenticity, and identification, confidentiality, integrity, data trust, and privacy. These are the basic security components that need to be deployed in any vehicular communication so that we'll have a secure, fast, and reliable V2X communication. So these are some of the attacks that affect the individual security components. So the security is important in V2X because V2X messages convey sensitive, life-critical, real-time information that needs to be secured against attacks. Because here in V2X communication, we are talking about information regarding the safety of humans trying to exchange between vehicles. So vehicles need to ensure the authenticity of the received messages before reacting to the received message. It has to ensure that the vehicle transmitting that message is trusted. It is a legitimate vehicle that is being allowed to participate in the V2X communication. So the security requirement between the vehicle-enabled device and also the EPC, which is the LTE core network, are mutual authentication between the vehicle and the serving network, confidentiality and integrity protection of the V2X messages. The third one is privacy protection of vehicles and vehicles users. So vehicles need to authenticate and verify their legitimacy with the network. Providing secure communication else is essential for the success of V2X. So basically, with related to V2X, LTE V2X communication, the LTE network has its own existing security infrastructure that is being used in the LTE architecture, which is the LTE AKA, which is LTE Authentication and Key Agreement Protocol. But this particular protocol, it does two things. One, it does the identification and authentication. And the second one is the key generation, in which these keys are being generated for subsequent confidentiality and integrity protection of the messages that travel across the network. So this LTE AKA protocol, that's the architecture of the LTE AKA protocol, is a challenge and response protocol, in which firstly the user, which is a vehicle user, it has already a permanent key and an IMSI, which is the identity of the vehicle. then it will send a request to the MME, then the MME will pass authentication data request to the HHS. At the HHS, it is where all the computation is being done using, it will generate some authentication vectors, which are the MAC, the expected response, the confidentiality key, integrity key, and the authentication token. So all these authentication parameters are being computed at HSS, then it will be then sent back to the MME, then the MME will then send an authentication request to the vehicle, and the vehicle user at the same time will have to do its own computation at its own site. So all this challenge and response protocol, challenge and response processes used to take a lot of time. Basically, it has been computed that the LTE AKA protocol used to take up to 300 milliseconds to make this computation, which is not accepted in V2X communication, in which the latency is very, very critical. Mostly the latency used to be, the maximum latency is 100 milliseconds in some use cases, but in others, maybe infotainment services, you can have up to 500 milliseconds. So this is the architecture of the LTE Authentication and Key Agreement Protocol, which is the underlying security mechanism that is being currently used in the LTE architecture. And any data traffic or any communication through the LTE has to leverage this protocol at the access security mechanism, that is from the physical layer to the MAC layer. So these are the challenges, these are the issues that are related to the LTE KA1. It reveals the client identity. As you can see from here, the IMSI, which is the client identity, is being transmitted in clear text, is not encrypted at all. So in that case, it breaches the privacy of users, or vehicle users, as we can say, and this means that a vehicle can be able to be located, or you can track a vehicle. So this is one of the issues with the LTE AKA. The second one is delay authentication procedure, which I told you, in which the computation of all these authentication vectors used to take a lot of time, which is, like I said, 300 milliseconds, which are unacceptable in V2V communication. The third one is absence of quick re-authentication during handover situation. Of course, in vehicular communication, you expect vehicles to be traveling from one E node B to another. So there is persistent handover between one base station to another base station. So during that handover, what happened is the whole procedure of LTE Yes, this whole procedure has to be established again during each handover situation, either inter-MME handover or inter-E node B handover. New session keys has to be established, in which there will be a lot of delay related to that. So, and there is also an overhead calculation in which the algorithm that does the computation are very, very complex, which need to be very lightweight in such a way so as to ensure reliability and fast communication in the LTE V2V. So the synchronization attack also is related to the attack that is being due to forward key separation and backward key separation during a handover situation. So what is required is enhancement and optimization to the authentication procedures of the LTE. Security protocol must be implemented with low communication overhead due to time constraint and low computation complexity to exchange quick and safe information in the overall LTE V2X. The security protocols must have minimal impact to the core network, because the LTE network is not only V2X that is going to be supported. There are other communication that is taking place in the LTE, because the LTE alone, there is also machine type communication in which the LTE is supporting it. So if there is much authentication signals, authentication requests that is going across the LTE core network, it's going to generate a signaling storm in such a way that it will overburden the HHS with a lot of authentication requests, which might lead to a denial of service attack. Also, the security protocols will comply with the 3GPP standard with minimal modification so as to get backward compatibility. So existing proposed solution in the literature that has been identified is one. So there are some that propose group-based authentication and key agreement schemes. Yeah, group-based communication, reduce authentication time and signal load to the HHS and MME, in which you have a cluster of groups in which one user can be authenticated on behalf of other users that are close to the clusters. But, and it also avoid congestion, but group formation is a bottleneck in V2X due to high mobility of vehicles. You can easily establish, form a cluster of vehicles within a particular area, because vehicles can join and leave the network as the case may be. So there's also enhancing the LTE using public key infrastructure. It incurs high computational communication storage and management overhead. Current method not fully satisfactory, so there is need for further research work on this aspect. So some of the proposed solutions are: one, moving the authentication vector generation to the MME using virtualization technologies. Second, optimization of the signaling handshake for connection management and authentication procedures, so as to reduce the time that is being used for computing the authentication vectors, and also leveraging LTE security mechanisms with software-defined network and network function virtualization towards 5G security innovation. The SDN and NFB are part of 5G security, that are part of mechanisms that have been proposed for 5G security, in which the LTE V2X is also part of the proposed innovation in 5G security. So the future work, this the research area has been established, the gap has been identified, and also the next thing is to design implementation of the enhanced security algorithms using appropriate components, which is currently what I'm trying to identify how to design and make the implementation as well. Maybe a simulation base or an applied project, as the case may be. So, and also testing and performance analysis to demonstrate future security features, that is robustness against attack, and also meeting the latency requirement of V2X communication. Thank you for listening.